have been leading for many years. We actually have two separate departments, polymer science, the one you see here. Right now I'm sitting on the 10th floor. We have also polymer engineering on the other side. And this is a graduate program in polymers. We get in total about 200 students in our graduate program. And the focus of this school is in both applied and fundamental science and engineering problems. On the applied science, we are looking at biomedical applications, energy, water filtration, adhesion. The adhesion is pretty much looking at, making a Spider-Man that you can climb on the wall. That requires obviously a fundamental understanding of how things are interacting at the atomic scale. So my involvement in this department and my research focus is on understanding how the interaction happens at the molecular and atomic scale. And we are using molecular dynamic simulation, and then we apply statistical thermodynamic principles to formulate a theory, either to come up with universal laws for polymers or to make some fundamental understanding to a class of polymers. Let me give you a background, a brief background of where I started. I know most of you are bachelor students right now, and there could be also a few master science students, maybe graduate students going to their PhD. Pretty much the path started long time ago. I got my Bachelor of Science degree from Addis Ababa University. The previous speaker, Dr. Daniel, was with my batch. Actually, I was looking to find this picture. I was asking him the other day. We couldn't, so luckily I found it this morning. And this is my classmates when we graduated with a bachelor's degree. Pretty much what we had, I would say that all the fun I had so far was in my undergraduate program. All my best friends are from this batch, coming from every part of the country, including as far as Eritrea, Asmara, and we have a lot of good time. And I tell you guys, undergraduate is the best time to have friends that you can establish for the rest of your life. So I did both my bachelor's degree and master's degree at Addis Ababa University. So after bachelor's, I was employed as a lecturer in the physics department at AU. And then a year after, I started my master's degree. When I was doing my master's degree, I got a chance to go to Germany to do my research work for 6 months in Saarbrücken, Germany. That's where I was exposed the first time the Western lifestyle. That was my advisor, Professor Wichert. This was my friend Yared. We went together, and these were group members. And what I realized after I came to the United States is that the European system is completely different from the American system. In Europe, your advisor is more like a father. You always, they take care of you, picking you up from the airport, and when you are returning, dropping you at the airport, and involving in your day-to-day life activities. And we had a lot of fun. I was also exposed to international students. Most of these were undergraduate students at that time, coming from Great Britain, Sweden, and a few other, Italy, and many different places. So I got the chance to understand the international dynamics. And more than that, this was the first time I was exposed to high-level research work. So I started to see how research is being done. The one problem I realized was that back at home, they teach us a very good mathematical skill, I would say, in terms of solving problems, but we lack the physical understanding, what their physical meaning. For example, if you take quantum mechanics, you solve Schrodinger equation, and then always you jump into looking at particle in a box. But nobody actually tells you in details why we are doing particle in a box and what its physical implication is. But my exposure to going to Germany and later on to the International Center for Theoretical Physics actually helped me to understand their physical meaning. Why are we solving those equations? What's their physical implication and so on? So I encourage you guys every time you go through these mathematical details, try to understand why we are doing them. Why do I go through all these calculations, which looks like abstract, but what's their physical interpretation? How does I connect it to the experimental data that are being collected in different laboratories? And that physical connection actually allows you the power of physics. That's what sets physics apart from mathematics. And my trip to Germany and ISTP actually helped me to understand the physical interpretation of all the detailed math that I did in my undergraduate and master's program. The International Center for Theoretical Physics, I encourage many of you to apply. Of course, they take 2 or 3 students per year from a given country. I think a maximum of 3, I suppose. But this is one of the best experience I had in terms of getting into the theoretical principles of physics. I would say that's where I established my foundation in physics, and that helped me where I am today. And immediately, obviously, allowed me to come for my PhD program to Case Western Reserve University in Cleveland, Ohio, which is about 40 minutes drive from where I am right now. There, I had a great chance to work in several problems. And actually, my advisor, Professor Philip Taylor, he recruited me during the first semester because with my ICTP strong background, I was able to skip some of the basic courses in that first year. So that allowed me to quickly jump into research work. So when I joined, the story behind it that when I joined his group, he asked me, what do you want to do? I said paper and pencil, which means sit down, solve problems. That's sometimes a kind of training that we get back at home. And then he said, great, we started doing that. After a year, he asked me what my plans are. Now I started to get comfortable with the American life. Then I said, oh, maybe I would like to do a postdoc after my graduation before going back home. Okay, he started to notice that the chance of me going back home is getting almost zero. In my research problem, so let me tell you part of the story. I'll get back to what I started. So I was doing this paper and pencil, and there came a time in which we need to do numerical solution. So I sat down, showed him the results, and then he said, I said, this requires, doing some kind of numerical calculation. Then he said, go ahead and do it. Then I said to him, no, I didn't have any programming background. I didn't take any programming course. His answer was simple. You are a physicist. Go ahead and train yourself for 2 weeks, and let's talk after 2 weeks. I told him again, I said, no, you can't take a computer programming course in 2 weeks. He said, go ahead and train yourself. That's what I did. I self-taught myself how to do programming. And as I told you guys earlier, I'm a computational polymer physicist right now. I have not taken any computational course. So that should encourage any of you, if you don't have any background, it's mostly hard work. You can bring it back. I have done, I self-taught myself C++ programming in a couple of weeks, and then was able to solve that numerical equation. And then as we get closer at the end of my second year, he said, if you are planning to continue or do a postdoc in the US, you want to expand your job opportunity. And he said, think about adding computational, doing some computational work. I thought about it for a couple of weeks, and then I came back and said, yes, I think that would be a great opportunity. That adding that component to my PhD work actually helped me to go to Sandia National Laboratories for a postdoc in Albuquerque, New Mexico. This national laboratory is joined pretty much with Los Alamos National Laboratories, which are about 50 miles apart. They have their own historical reasons, but it was a great place to do a postdoc. I worked on mostly on the applied part of polymers. Every time we are applying statistical and thermodynamic principles to what we are actually doing. Then after postdoc, I was hired in a physics department at Southern Illinois University. where I was assistant professor, and as soon as I was promoted to associate professor, I moved to the University of Akron. They were looking someone with a polymer background, and in the University of Akron right now, I'm dealing with a very good group, diversity of students from different parts of the country, including from Ethiopia, of course, mostly China, and we have Indian students and also Iranian students. This is the picture that was recently taken. As you can see, this is during the pandemic. And my group's focus is to use computational tools. I'll try to see maybe one problem, how we do it, to understand how things are happening at the atomic scale. So pretty much this was my path from my bachelor's degree to where I am today. Okay, let me just briefly tell you the outline. Polymer physics is a separate field. In our case, our students take 1-year course to get involved in any polymer physics research work. It's very wide. So I cannot tell you the whole story, as you could imagine, in 1 hour, but I'm gonna give you a brief background, why polymer physics is needed, what it is focusing on in general, in terms of our understanding of polymers. I'm assuming that most of you, if not all of you, have a good understanding of chemistry, and polymer is pretty much what we call a long molecule, something like that. And the focus is how do we understand what we call the conformation. It's going to take different shapes. So I'm gonna walk you through what are the foundations in polymers. First, define what they are. Second, what are we trying to understand? And third, what's the contribution? In the process of doing that, I'll be introducing what's known as glass transition temperature, which you probably may not know, but I know everybody knows what melting temperature is. There is a huge difference between the two. So if you guys have any questions, stop me at any time. There is no need to make it formal. I'm assuming this is informal, which means if you get confused, just stop me and ask so that I can explain better. Okay, well, polymers, I'm sure most of you know macromolecules. Macro, large molecule, a much larger molecule. Polymers are also called, they are macromolecules, but what makes them different is that they have what we call mers, or a monomer, a unit that's repeating many times. Poly means many in Greek, mers means parts. So we are saying you have many parts of a certain repeating unit. Let me walk you through the simpler macromolecule that you know, which is polyethylene. It has a CH2 group over here. Now, when you are repeating this one, you get what's known as polyethylene, poly money, and it becomes a polymer because you have a repeating unit. And of course, as you can see, if I have thousands of this one, I'm not going to write it this way. It gets complicated. This is one simplified version. Obviously, if I have 1,000 of this one, it's going to be very long, but then you are representing what's known as the monomer unit multiplied by the number of units that you have. So we call it polyethylene. Of course, we have different types of this one. Polystyrene is what you guys are encountering on a daily basis, the plastic bag that you have, and maybe the use and throw cup that you are using. Everything is polystyrene. Polymer is all around us. Mostly the tires that we see everywhere are completely polymers. If you look around you, the chance is that 75% of the time you have polymers. You are encountering the clothes that you are wearing. Most of our proteins and so on, they are also polymers. And as a result, what we are looking at is what's the repeating unit. So once you identify the repeating unit and you say, if I have many numbers of this one, I have what's called a polymer. Now, let me take the simpler polymer that we talked about, polyethylene, CH2. Chemically, it's simple. Now, without changing the chemistry, what we are changing is the number of units that you are connecting. If I have a polymer, in most cases, we shouldn't call it a polymer. If it is a short chain, we call it oligomer. If I have a unit consisting of 1 to 5 repeat units, that's very short. We find it in a gas phase at room temperature, and that we call it propane. Propane is what we use for cooking, the cooking gas that we have. Now, without changing the chemistry, still we have the CH2s, but we make this polymer chain longer, go from 1 to 5 to 615. Now, at room temperature, what happens is that it becomes a liquid, a low viscous liquid, and this is what we call gasoline. That's the one we use for driving our cars. So chemistry-wise, they are the same. The only difference is that the molecules are getting longer and longer. As a result, you go from a gas phase to a liquid phase. If we make it slightly longer, now it becomes very viscous, and this is what we call motor oil. And the same thing that we use to lubricate our cars. If I make it slightly even longer, now it becomes a soft solid. And that's a paraffin wax that we usually use for candles and sometimes for coatings. Well, in the experiments, you can make them even much, much longer. That's the balloons and the plastics and other things that we are actually making. These are called polyethylenes. And pretty much these different scenarios for a simple chemistry is just how the polymer chains are behaving. Now, the physics, the polymer physics behind it here is one, what's happening with the density. So what you are realizing is that as I make the polymer chain longer and longer, the density is actually changing. We go from a gas phase to a tough solid, and that change of phase or change of density is what's pretty much defining on what kind of application that we are actually using. And that is the understanding that we wanted to have on the polymer physics direction. I'm gonna be a little bit technical because if I tell a story about polymers, I have to tell you that there are several classes of polymers. Let me see where it's going. We have what's called homo and heteropolymers. As I said, by connecting monomer units one after the other, you make a polymer, but we can have different kind of monomers. I can have ethylene, styrene, I can connect both of them together. That gives me, depending on the connection, either homo, which means one type, or could have hetero, which is multiple type. So if I have the same monomers connected, it is similar to the story I told you in the previous slide, which we call it polyethylene, polystyrene, and so on, one unit. But I can have the option of connecting one unit with the other in alternating, so we call it alternating block of polymers, or I could have one on the backbone, the other one on the side chain. This is called grafted. I could have random orders, or I could have one polymer on one side, another polymer on the other side, and we call it diblock, triblock. It comes in different components. Actually, this is where the application, having just a single one has limited application, but when you make them more in this format, the application of polymers becomes very wide. So on the electronic side, as you know, we are making things smaller and smaller. And the only way we are able to get into nanoscale in the order of a few nanometers. These days, the requirement is actually going down to 5 nanometers. That is only possible by going into heteropolymers, because these polymers have huge application in the electronic industry, where you can actually transfer patterns from one form to the other. And that's achieved by going through this kind of what we call heteropolymers. Now, the question, as you see in this design, what this brings in is what we call architecture. Now, what chemists synthesize they can actually synthesize different architectures of polymer. It could be a linear one, just a linear, more like a string. But at the same time, as I said, you can actually design different forms. You can have a linear one. You attach chains on the side. We call it, it looks like more like a comb, but this is a flexible comb. Or you could be having a center, large molecule, and you attach polymer chains around it. This is called a star polymer. Or you can avoid the ends of your linear, you form a ring. The options are huge. This is not just hand drawing. This is what chemists can actually do in their laboratory. They can produce all this structure. Actually, the structures, even more fascinating structures can actually come. They can twist these polymer chains to catenate them. You can mechanically interlock them. And this new class of polymers now are actually pushing us to a different direction. One, in terms of water filtration, that means you want to remove contaminants on the surface and you allow the pure water to pass through. That requires having a different components of polymers, one that likes water, the other one that hates water. And the two actually play this great role in terms of purifying water. Of course, in most cases, you are controlling the different components that you have to achieve a certain kind of application. So where we get into is, okay, we have all these complicated polymer types. How do we understand them? So let me tell you a simple example. You can think of polymers like a pasta, like this one. When you boil them, they are pretty flexible. And then when they started to cool down, that means as you reduce the temperature, they start to dry, they become rigid, and they form this kind of structure. So when they are in that form, we call them amorphous. Amorphous because they don't have any structure. And that amorphous structure of polymers has its own huge application. So the rubber, everything that you know about that bounces back and forth, they are in this state. They have to be in that floppy state because they are more like soft. Now, when you go to this dry state, they could be in a crystalline because they are well ordered, or they could be in that amorphous state but still less mobile. This becomes a solid state. These two are very, very different. Now, what polymer physics, the whole idea about polymer physics is to look at the conformation, what kind of conformation of a polymer chain takes in all these different structures. Let me tell you what conformation means. I have, I think, a movie over here. Do you guys see my screen?
Yes.
Okay, great. So here what I have, let me look into. So I'm showing you a simple okay, this is a simple polymer chain. It's called polyethylene oxide. It is used for biomedical application for implants, mostly in the knee, to carry stress while we are walking. And some of the challenges this has is it likes water. So our body is 75% water, so it's going to dissolve. So obviously, in our case, we have to come up with a mechanism to keep this material stable. And the basic understanding starts from looking at the single polymer chain and see how it's behaving in different kind of environments. The first one will be in aqueous solution, that's water, and you can actually change the solution environment and see what kind of conformation it's taking. Okay, so so this is the computer simulation work that we have done to understand the solution properties of this polyethylene oxide. And now this is actually surrounded by a lot of water. And what you see is, this is looking at the molecule, which is about 5 nanometers in size. So you are looking at things at a nanoscale and following it in the order of a picosecond. So a picosecond is 10 to the power of minus 12 second, and a nanometer is 10 to the power of minus 9 meters. So that's the molecular level information that we are looking at. So what happens is that this molecule is surrounded by water. It keeps on changing its structure, which we call conformation. And that change in conformation can be actually associated with its physical properties. So pretty much when we are looking at the details of these molecules, what happens is that it has a helical structure, as you see here. So the helical structure is what we are looking at, and it's completely stretched out, which means it likes to be surrounded by water. So every time when a polymer likes what kind of environment it is around this, it starts to stretch out. And of course, the probability of completely stretched out is almost zero, or a very low chance. Now, what we do is we bring in statistical mechanics, because in the statistical mechanics, every frame that you see is the microstate of your system. And that microstate can be described by a few physical parameters. That physical parameters could be what is the size of this molecule. The size from your first year physics course, as you remember, can be done through what's known as the radius of gyration or moment of inertia. You can bring in that radius of gyration idea to characterize your molecule. The eigenvalues of your moment of inertia or radius of gyration tells you what kind of shape your molecule is actually taking. Is it more like spherical, collapsed, or prolate, oblate, spheroid? Those kind of characteristics are actually helping us to understand the structure of this molecule under different environments. If I take this same molecule and actually put it in a different solvent, toluene with water, this molecule forms what's known as hydrogen bonding. I don't want the time to get into, but if any of you guys know what hydrogen bonding means, it forms and breaks some quasi bonding with the oxygen atoms of the PO. Now, when you put it in toluene, toluene is a good solvent, but not a very good solvent for PO. It changes from a completely stretched state to a slightly collapsed state. So you start to see a change in the microstructure of this molecule. So when I take a different snapshot, this frame, and analyze its data in terms of its size, how it's breaking hydrogen bonding, the helical structure, the different conformational states, then the thermodynamic properties of this polymer is very different. That thermodynamic parameter understanding based on statistical mechanics is what we are actually using to interpret the physical properties of a given polymer. So in our case, we can look at, if I start cooling this molecule down, change the temperature down, what happens is that its dynamics will slow down, and at some point it actually completely stops in the time scale of a second, maybe even in a minute, but in a much longer time scale, there could be some kind of motion. But now you see that its structure is completely different from what I showed you in water. That interpretation is what we need to understand the behavior of this molecule in different environments. Now, you take that single chain, the one I showed you, and you surround it with similar chains around it, because that's what happens over here. Now, what happens is that because these chains are very long, they start to entangle. As you see, there is some kind of entanglement. That's what makes the mechanical properties of polymers very different from others, like ceramics. For example, ceramics, if you deform them, they break quickly. Whereas in the case of polymers, if you deform them, you can stretch them much longer because of this connectivity entanglement behaviors that we have. It gives them that mechanical strength. Now, the question we ask is, well, polymers never straight. The probability of being straight is very low because, as you know, entropy is at play. The entropy says that if I'm in that stretched state, it's going to be zero. We know that systems want to maximize their entropy. You don't want to go to zero entropy. So they usually stay in that flexible state so that they can access different microstates. As a result, they maximize their entropy. So we know that going in that state is usually very low. Even in the crystalline state, they are folded many times. Now the question we ask is, how much is polymer bent? That is one of the parameters we answer through polymer physics. This is actually the foundation, the first starting point, not getting into the complicated one, which would be easier for me to explain to you guys in this short time. Then we ask, what's overall size? Can we determine the overall size of a polymer? Theoretically, yes. What about, can we measure it? And of course, what are the parameters that are actually going to affect it in terms of, the kind of solvent I showed you, the temperature, and a few other parameters. From the theoretical side, you can have different ways of doing it. One way is what we call the end-to-end distance. That means if I take a polymer chain, I have one end, I have the other end, I can follow that. But what you realize from the movie I showed you earlier is that this end-to-end distance keeps on changing. So if I take the average, it's going to be zero because they start to cancel out. So that end-to-end distance is not a good parameter. The one to look at will be a non-vector, which means take the square. Take the square of your end-to-end distance. That becomes positive all the time. So it can be used as one parameter. The challenge is they cannot measure it experimentally. Experimentally, it's very hard to measure end-to-end distance. Instead, what they can measure is what's known as the radius of gyration. The radius of gyration at this atomic scale, what you are doing is you take the position of a given atom, then you subtract out the center of mass of your polymer chain squared. And then when you add up that one multiplied by the number of subunits that you have, it gives you the size. That can be measured through diffraction approaches, X-ray diffraction, neutron diffraction, and so on. So you can actually directly compare with experiments. Well, on the theoretical side, the approach of doing size calculation is very easy. These are the simple equations that I'm showing you. The challenge comes on the experimental side. How do we do it? Okay, first let me show you, what kind of sizes that we are actually talking about. If I think of a monomer, a smaller unit, in the order of about 1 angstrom. Usually they are much larger, but I'm looking at the smallest unit, polyethylene, the carbon-carbon bond, which is in the order of 1.4 angstrom. And usually the number of monomers per chain that we find could be from 100 repeat units to maybe 1 billion or more. And of course, the length scale that we are looking at now could be it could vary from 10 nanometers to 1 meter. The question is, how do I have this variation? If I take this chain and drop it into what we call a poor solvent, that means the polymer doesn't be surrounded by solvent. What it does is it goes to a collapsed state. This collapsed state for this longer polymer would be in the order of 100 nanometers. You are in a nanometer scale. If I take this same polymer, but drop it into another type of solvent, which is, the polymer doesn't either like it or hate it, we call it a neutral solvent, then we go from 100 nanometers to 10 millimeters. If we take the same chain and drop it to what we call a good solvent, then it starts to swell, and the size changes to 100 millimeters. Now, this millimeters, this is in the length scale that we can actually see. Actually, if I drop this into a charged solvent, if my polymer is charged, if I have a strong electrostatic interaction, then it actually completely stretches out. That goes to in the order of a meter. So the same polymer chain either collapses to a collapsed state, we call it globule, in the order of nanometers, or it could be stretched and become 1 meter. The polymer physics tells us why this is happening. It tells us a general universal properties of polymer, which says if I have a polymer in a poor solvent, its size scales as n the power of 1/3, where n is the number of repeat units I have in a polymer. If that polymer is placed in a neutral solvent, instead of n 1/3, it scales as n 1/2. That means it becomes larger. In a good solvent, it becomes n to 3/5, and in a long range repulsion, it becomes linear n. The beauty of the polymer physics is that it doesn't take the chemistry into account. What polymer physicists established a long time ago is that polymers behave identical, and their most important parameter is connectivity, how long they are. And their chemistry comes in terms of what's called stiffness, how stiff your polymer chain is. The model developed says, if I reduce all polymer by their stiffness, they get into some universal properties. And that universal properties gives us this beautiful equation, which we call scaling laws. And the scaling laws are the foundations that we all establish in polymer physics, trying to interpret experimental data. Now, if you bring in any kind of polymer, you do the measurement, they always match with this theoretical prediction. And actually, this allows you to understand whether you are dealing with a poor solvent or a good solvent or the type of solvent that you are going to have. Now, the question one would be asking is, how do I separate these chains? We are talking about single chains. How do you do that in the experiments? The experimental approach is quite easy, which means you put a lot of solvent into your polymer system, and they do it in a good solvent. So I'm going to walk you through to a simpler approach of doing that measurement. For example, take the polyethylene oxide, the movie I showed you, in water, put thousands of them, but you have a lot of water. So what happens is that they go, each chain separates away from each other because they want to be surrounded by water molecules. They form what we call like clouds. You have patchy clouds forming, and that is more like having their own spherical size moving around. Now, when you do diffraction, either neutron diffraction or X-ray diffraction, they can actually separately access these single chain properties, okay? So that first step is to get into that dilute solution. The dilute solution is the region in which you are actually separating individual polymer chains. You are not, this is not possible in a poor solvent, because if you put it in a poor solvent, you have precipitation. Precipitation means they condense down, they separate. There is a phase separation between your polymer system and the solvent. So as a result, now by separating in chains, we can actually determine their structural properties, their single chain properties. What are those properties? One could be looking at their molecular weight. That's done by light scattering, both static and dynamic. You can measure their chain lengths, again, using scattering techniques. You can find the shape of these polymer chains, applying scattering methods. You can also look at molecular weight distribution. If you have a heteropolymer, you can look at their chemical heterogeneity. And of course, you can also measure how they are diffusing in your solvent, how they are moving around. All this can be directly captured with the kind of computational work that we are doing. So in our group, we have pretty much access to all this kind of information that we can directly compare with the experimental groups. But our simulation also allows us to go beyond what the experimentalists can do. Remember, the experimentalists are getting this information indirectly. Indirectly means they shine light, and the response from that light is what they are interpreting. Of course, from your quantum mechanics, the Heisenberg principle, you know that every time you change the state of your system by shining light, the system is not really the same. Of course, the assumption taken by the experimentalists is that the change of the state by shining light is very little. In the simulation, we don't need to do that because we know the position of the atoms, they are evolving, and their velocity. Then statistical mechanics tells me that I should be able to determine any observable properties of that system, period. That's the whole idea of statistical mechanics. We can apply statistical mechanics, taking the position, velocity of the atoms, generate different autocorrelations, and that allows us to determine the thermodynamic parameters. And those thermodynamic parameters exactly tell us what the physical properties of those systems is going to be. I think, shall I continue? What's the plan? Dr. Dereje?
Have another 5 minutes.
Okay, great. Okay, so now let me take you to the basic principle of polymers. When we are looking at polymers, their application comes from their structure. As I was telling you, these are very long polymers. Now, what you are looking at is what's their physical properties at room temperature, because that's the application that we are looking at. How do they behave? Well, some polymers may be solid-like. I think any plastic that you touch may sound solid-like, but as I said, it's not solid-like, but it's soft. Pack. Because they are long, getting into a well-ordered structure the chance becomes very small. So in effect, what you are getting is what's known as a semi-crystalline solid in most cases. Semi-crystalline solid means part of your system is crystalline, nicely packed, the polymer chains making that zigzag structure. And the other part is amorphous, not ordered. Both can be identified, their volume fraction in the system through experiment and simulation. That information is quite accessible. The two behave differently. This, we call it behaves like amorphous. This behaves like crystalline, and crystalline and amorphous behavior is completely different. And that comes into the important parameter of what's known as glass transition and melting. The melting temperature, as pretty much all of you guys know, let's say if I heat ice, it melts at around 0 degrees centigrade, which means it breaks down from a very ordered, structured ice structure to a disordered water. That's in a melt state. And melting, as we know, is a first order phase transition. That means it has all the characteristics that we know about first order phase transition. That is the characteristics of any crystalline materials, including polymers. So the crystalline part of a semi-crystalline polymer shows a melting temperature. It melts at some point. But the amorphous part shows very different because it's not crystalline. We cannot talk about melting. Its behavior is described by what's known as a glass transition. That means if I heat it up, that amorphous part, which behaves like a solid, it actually starts to vibrate. It forms what we start to know segmental motion. It becomes kind of soft. Where that happens, we call it a glass transition. The reason we call it glass is there is no change in the structure. Still, it's amorphous. The only change that we have is in dynamics. So glass transition is purely a dynamical process. We have known glass for more than 100 years. It is still an open question. We have no answer why it is happening. We come to understand that it's not really a thermodynamic transition like melting, because the glass transition temperature depends on the rate of heating and cooling. For a phase transition, it shouldn't happen. That's what makes it an open, the number one open question in material science. Very complicated problems, theories have been formulated, but none of them can help us to completely understand the glass transition properties. So as a result, we are always trying to understand a little piece of here, a little piece of that, but putting all that into one theoretical principle has been lacking. Well, so what's a glass? The amorphous part, as I said, as I heat it, it becomes slightly mobile liquid that we call it rubber. So above that glass transition temperature, it behaves like rubber, soft, and so on. Below that, it behaves like a solid, but on a thermodynamic sense, it is actually glass, different from the kind of crystalline solid that we know. What's the difference between glass and crystalline? There is a huge difference. Glass is in the time scale that we are looking at. We believe it behaves like solid in a few hours. So it is frozen in place, but its structure is like liquid. Actually, if I take water and quench it below zero quickly, instead of becoming ice, it can actually become glass. It become glass means it kept the structure of the liquid water without rearranging in that tetrahedral structure. The ice had nicely packed tetrahedral structure. You find that when you slowly cool it, but if you make it fast, you actually go from a liquid water to a glass water, which are the same structure, but in a solid state. And in that solid state, it's frozen, but they slightly vibrate. If I were to take frames over 100,000 of years, they actually behave like a liquid. You can see the difference. I think the best way to look at this one is take a chewing gum. If you take out a chewing gum, slowly stretch it, you can actually stretch it. If you stretch it fast, what it happens is that it breaks like a solid. Those are the time scale that we are looking at. How fast I pull it can determine actually whether my gum to behave like rubber, because you are chewing it, it's more like rubber, or behave like a solid because I made it fast. The time scale is key. So if I were to take pictures of my glassy polymer system every 1,000 years, it actually looks like that it's flowing like a liquid. Its structure is like a liquid. So glass, we call it a frozen liquid. And all the characteristics, the application that we know about polymers comes from this glass state. This glass state is key. Okay, what are the principles? You come up with a new kind of polymers. The first thing you need to do is find out where the glass transition is happening. That means at what temperature it behaves, it changes from a glass state to a rubber state. That's key, because you wanted to know, depending on the application, whether you want it to be soft or hard. If it is not in the domain that you want, there are ways of shifting the glass transition temperature of your system. I don't have the time to get into, but one of the things is what we call plasticizers. A good example would be, if you look at the car, the dashboard on our car, that one, it is rubber. It stays rubber in a very cold weather. Of course, in Ethiopia, that's not a problem. But in the northern hemisphere, the temperature in the winter time can go several degrees below 0 degrees. And in the winter, it goes in the order of 40, 45 degrees Celsius. So you have huge change. In that huge temperature, you want to keep it in that rubber state. And you add what's known as plasticizer. These are small molecules that wants to keep your long polymer chain system in a rubber state. That's why when you enter a new car, it had that unique smell. That smell is actually coming from the plasticide, those small molecules evaporating from your dashboard. So over time, your dashboard gets older and it starts to break when it loses its glass transition temperature, unique properties at that particular temperature. So those are some of the applications that we are looking at. I think according to Dr. Dredge, probably my time is up, and maybe I'll open the floor open for questions.
Thank you, Dr. Mesfin. There is one question on the chat.
Okay.
From Solomon Hailemariam from Jimma University. He's a PhD candidate. It says, the beauty of polymer simulation is determining noble properties of materials by simulation beyond experimental. How can we check if it is beyond experimental result?
Oh, okay, that's a very good question. One, if simulations couldn't go beyond what experimentalists can do, then our existence would have been under question. Because if the experimentalists can explain everything, then they wouldn't need us. As I was trying to show you, in the simulation, we are looking at things atom by atom. So when I have, for example, most of the material science problem that we are looking at these days is how two interfaces interact with each other. When I bring one system on another, any application that you think of these days consists of different layers of films. And those films interact at the interface. Characterizing that behavior on the experimental side is very challenging. It's called buried interfaces. Buried means very hard to access. The only way you interpret the experimental data is from their macroscopic behavior. How do they respond to some changes? But what happens at the molecular scale, how they are interacting with each other, that information can only come from the simulation. The simulation side, of course, one could say classical simulation versus quantum. That's a difference of a length scale. Both have their own advantages and disadvantages, depending on the length and time scale that you are looking at. So without any doubt, the simulations are key in providing those atomic level information that's extremely hard to find from the experimental approach. And that has been the approach pretty much these days. Experimentalists, when they come up with some kind of observation, they immediately come and approach us and say, can you explain what's going on here? If I have a theoretical explanation that I can quickly provide, I do. If not, we study them on our computer. When I say study, we have a model that nicely describes each polymer system. Then we pretty much say the reason you are observing this kind of properties is because these functional groups interact in a different way than what they may have suspected. So in short, simulations are key for providing those atomic molecular level information for the experimentalists.
Thank you very much, Dr. Mesfin. Let me see if there is a question on Slido. Zalalam, are you listening? Or Eden? Okay, that's all the question then. And thank you for your presentation, Dr. Mesfin. We really appreciate it.
Excellent. If any of you guys want to ask more questions, you can reach me by email.
Right.
I think that's actually provided in the website. And enjoy the rest of the day.
Thank you very much. Okay, this is the end of the second day of VSS. We'll see you tomorrow morning at 9 a.m. At this time. Okay, bye everyone.
Okay, bye.
Bye, bye.
Bye.
Bye, guys.
Thank you, guys.
Thank you.